All right, so we're focusing on graphs of polynomial functions. Specifically, we're going to look at recognizing characteristics of graphs of polynomials, factoring to find the zeros of polynomials, and looking at end behavior, finding those zeros and their multiplicities, understand the relationship between the degree and the turning points, and the multiplicity and what happens around the zeros and the intermediate value theorem. And a lot of this stuff was introduced in the prior section. So we're going to just go into a little more detail here. So with polynomials, remember that the graphs of polynomial functions are smooth. That means they don't have any discontinuities. They don't have any jagged, sharp edges. And they're continuous. They don't have any breaks. So they're not like piecewise continuous functions. So because of that, we can find zeros of a polynomial by factoring the polynomial and setting it equal to 0. And then, we'll set the polynomial equal to 0, then factor out any common monomials. Don't forget about those, because if there's an x in that monomial that you factored out, that means 0 is a root, right? Some people forget those. Factor any remaining binomial or trinomial and set each factor equal to 0 to find the root, which is also called a 0, which is also called an x-intercept. They'll pretty much mean the same thing. So, leading term test, of course the domain for a polynomial function is going to be all real numbers, right? And the leading term dominates, right? Dominates the polynomial, dominates the behavior of the polynomial as x becomes very large, because 10,000 to the fourth is way bigger than 10,000 to the second or the third. So it's like when you get into really big numbers, the only thing, the primary thing, the biggest thing that matters as far as the graph goes is that leading term. All the others become small potatoes comparatively. So with that knowledge, we can look at this particular polynomial and say, okay, what's the leading term? And we're going to say, well, let's see, what's the highest power? Right? The highest power is going to be 5. So this is a 5th degree polynomial. And the leading term is going to be whatever term has that highest power. Pretty simple there. Our domain, like all polynomials, is going to be all real numbers. And now we got to talk about the end behavior, right? So what do we remember about x to the 5th? We remember that odd power functions go opposite directions, right? That x to the 3rd looks like this, and x to the 5th, or x to the 7th, or x to the 9th, or whatever will all have that same general shape in the long run. And it's just a question of whether or not it's been reflected. This one has not been reflected. So we can say as x goes to negative infinity, so as we go out this direction in x to the left, our function is going down. Y goes to negative infinity. And as x goes to positive infinity, we're going to say, actually I don't need to rewrite that because it's right there. We're going to say y goes to positive infinity, right? Because as we go this direction out on our curve, our function is going up. Okay, so pretty straightforward there. Now, when you get asked to sketch the end behavior, let's see here. There we go. We don't know yet what might be going on in the middle, right? We know that there's a max of 5 x-intercepts because it's going to be the same as the degree of the polynomial, and that there's a max of 4 turning points. But in the long run, right, we know it's going to go up as x gets large. We know it's going to go down as x gets negative, more and more negative. And in the middle, we don't really know what's going on. So right now we're just going to be like, whatever, could be that. So, all right, so let's work on another one, right? This time, we say, okay, what's our leading term? We're going to say, okay, great. I have a highest power of 4. So 4th degree poly. And so our leading term, negative x to the 4th. And again, we know our domain, it's a polynomial, therefore the domain is all real numbers. And our long run behavior, so we know, so even power functions, we know are going to have both, and they're basically going to look like some version of a parabola. So both ends are going to go in the same direction, but this one has the negative leading coefficient is going to cause a reflection, right? Reflect over the x-axis. Let's write that better. Okay, so we know that as x goes to negative infinity, that y will go to negative infinity. So we've got y. So we know this one, long run end behavior, we know it's going to be reflected over the x-axis, so we know y will be going to negative infinity, whether x is going to positive infinity or negative infinity. So we're going to write that. And sketch end behavior, well, I already did that, but we know we have we have a max of, let's see, 4 zeros and 3 turning points, right? We actually do know one of the zeros here because we look at this and we say, every one of these terms has an x in it, so I can factor that out. So we know that there's a 0 at x equals 0, and there's a maximum of 3 others, right? So, let's see, it could do something like this. Wait, let's see, 1, 2, 3, 4. Yeah, there we go. It's okay. So something like that. We don't know exactly because right now we're not focusing on the zeros. All right, so that'll be it for this one. Next up is zeros of polynomials.